Imagine the year 2026. Global Tier 1 financial gateway suddenly halts. Millions of transactions are stuck in a pending state, and the error logs are filled with logic branches that no human developer ever wrote. This is the ghost code incident. During the peak of the vibe coding craze in 2024 and 2025, developers relied heavily on LLMs to generate complex asynchronous logic through casual prompts, just vibing with the AI until the code seemed to work. But without a structured architectural blueprint or rigorous traceability, these systems became ticking time bombs of technical debt. When the underlying LLM models updated or edge cases shifted, the black box logic collapsed. We are now witnessing the first wave of enterprise-scale systemic failures where the cost of debugging exceeds the initial speed gains. This isn't just a bug, it's a fundamental breakdown of engineering accountability that threatens the very foundation of modern software reliability. But what if I told you this disaster was entirely preventable by changing how we perceive the AI as a partner relationship? By the end of this lecture, you will see exactly how to prevent this ghost code from haunting your own architecture. To survive the post-hype era of AI development, we must pivot from vibe coding to a disciplined, sustainable AI-assisted engineering methodology. Architectural integrity cannot be sacrificed for temporary velocity. True engineering rigor involves more than just getting a prompt to work. It requires a systematic approach to prompt versioning, automated verification of AI-generated logic, and the maintenance of a human-readable knowledge graph. Industry experts and professional engineers are now calling for a return to fundamentals, but integrated with the power of generative models. This lecture will define the bridge between the chaotic speed of AI prototyping and the stable requirements of enterprise-grade systems. We will move beyond the copy-paste culture and establish a framework where AI serves the architecture, not the other way around. By the end of this session, you will understand how to build systems that remain maintainable, even when the AI that helped write them is long gone. But before we build the solution, we must understand the specific mechanics of how vibing actually destroys your codebase, which we will examine in the next chapter. The rise and fall of vibe coding. To understand the current crisis, we must first define the phenomenon of vibe coding. Traditionally, software engineering is a deterministic discipline grounded in formal specifications, rigorous logic, and predictable state transitions. However, as large language models like GPT-4o and the early Claude 3.5 Sonnet became ubiquitous in 2024, a new paradigm emerged. Vibe coding is a development style where the primary interface is natural language, and the success of a feature is judged by its immediate feel or vibe rather than its adherence to an architectural blueprint. In this era, developers began acting more like curators of AI-generated output than architects of logical systems. While this significantly lowered the barrier to entry for rapid prototyping, it introduced a dangerous level of abstraction, where the developer often does not fully comprehend the underlying logic being executed. This shift from code as intent to code as suggestion is the foundational shift of the 2020s. But how did this reach a fever pitch before the inevitable crash? Let's trace the timeline of this intoxicating surge. The journey to our current state in 2026 was paved with rapid milestones. In 2023, the industry focused on RAG and simple chat interfaces. By late 2024, we saw the rise of agentic workflows where AI began to self-correct and execute multi-step tasks. This led to the great vibe boom of 2025. During this period, enterprise productivity metrics initially skyrocketed. Startup burn rates plummeted as teams of 2 could build what previously required 20 engineers. The industry was blinded by the productivity illusion, the belief that the speed of code generation was equivalent to the speed of value delivery. Major tech hubs began prioritizing prompt engineering over software architecture, leading to a massive influx of code that no human had fully read or vetted. We ignored the historical lessons of the silver bullet, believing that for the first time, we had truly decoupled the complexity of software from the human capacity to manage it. The speed was intoxicating, but it obscured the crumbling foundation beneath the surface. Does this high-velocity output actually scale for long-term maintenance? Let's analyze the psychological trap involved. The core problem with the vibe coding era is the dramatic reduction in cognitive load at the point of creation, which paradoxically increases the maintenance step later. In standard software engineering, the difficulty of writing code serves as a natural filter. It forces the developer to think about structure, data types, and edge cases. Vibe coding bypasses this filter. When an AI generates 500 lines of Python or TypeScript in seconds, the human reviewer experience is subject to confirmation bias. If it runs and looks correct on the surface, it is merged. This creates a false sense of security. Developers stop engaging with the leaky abstractions of their frameworks. According to ISO EEC 25510 standards, software quality includes maintainability and portability, both of which are sacrificed when code is vibed into existence without a structural plan. We are essentially building skyscrapers with 3D printed materials we don't understand, hoping the internal physics will just hold up. When we stop reading what the machine writes, we lose the ability to manage the very debt we are creating. But what exactly does this new form of debt look like compared to the debt we've known for decades? Technical debt is a concept as old as programming itself, but AI-induced technical debt is a different beast entirely. Traditional debt is usually a conscious choice, a shortcut taken to meet a deadline. It accumulates at the speed of human typing. AI-induced debt, however, accumulates at the speed of GPU inference. It is often silent debt, where the code follows no consistent pattern because it was generated across different chat sessions or by different model versions like GPT-4 versus Llama 3. While traditional debt might involve a messy statement, AI debt involves entire modules with leaky abstractions that only work under specific narrow prompts. This entropy spreads through your enterprise architecture like a virus. It increases the maintenance cost exponentially because no single human has the mental model of how these disparate pieces truly interact. This debt isn't just a maintenance cost. It's a structural collapse waiting for a single context window failure. Let's visualize how this fragmentation occurs across a real-world codebase. The most insidious aspect of vibe coding is context fragmentation. Even with context windows reaching millions of tokens, an LLM still lacks a holistic, persistent understanding of a 10 million-line enterprise codebase. When a developer works on a specific feature, the AI only sees a slice of the architecture. This leads to spaghetti prompts, where localized fixes break global invariance. For example, the AI might suggest an optimized data structure in Chapter 1 that completely violates the security middleware established in Chapter 5 because that middleware wasn't in the prompt's context. We see a loss of conceptual integrity, a term coined by Fred Brooks that remains vital today. The architecture becomes a collection of local optima that create a global disaster. Without a central source of truth that governs how the AI generates code, the codebase fragments into thousands of inconsistent styles and patterns. And as the architecture frays, the most critical layer of your enterprise security begins to develop invisible cracks. Finally, we must address the security blind spots introduced by blind trust in AI suggestions. In our consultancy work, we see a recurring pattern of hallucinated dependencies. AI models often suggest libraries that don't exist or were deprecated years ago for critical vulnerabilities. Because the developer is in a vibe flow, they might run npm install or pip install on a package suggested by the AI without realizing it's a typo-squatted malicious package or a non-existent one that a hacker later registers. Furthermore, AI often simplifies code by removing essential sanitization or hard-coding sensitive keys just to make the example run. Following the NIST Cybersecurity Framework 2.0, we must recognize that AI-generated code represents a significant supply chain risk. Trusting the vibe of a piece of code while ignoring the rigorous validation of its security posture is a recipe for catastrophic data breaches. These vulnerabilities are the first symptoms of a deeper rot, which we will categorize in the next chapter as the 4 distinct mechanisms of AI-driven decay. The first mechanism of decay begins with the erosion of the system's structural integrity. When we engage in vibe coding, often focus on solving a localized problem through a specific prompt. However, AI models tend to prioritize local optimization over global architectural alignment. In an enterprise environment using clean architecture or domain-driven design, the AI might suggest an active record pattern or a singleton that violates your dependency injection rules simply because it looks like a valid solution. This leads to what we call architectural drift. Over time, the gap between the intended design and the actual implementation grows so wide that the system becomes a big ball of mud. Professional engineers know that the cost of a system lies in its 10-year maintenance, not its initial creation. If every feature follows a different AI-generated whim, refactoring becomes impossible. But the problem doesn't stop at the structure. It invades the very safety nets we use to ensure code quality next. We look at the testing trap. High-quality software is defined by its testability, yet vibe coding frequently produces test-resistant code. The AI might provide a script that executes perfectly in a demo environment, but when you attempt to write a unit test, you encounter deeply coupled side effects and hard-coded dependencies. This is what we call mocking hell. To test a simple 50-line AI function, you might end up writing 200 lines of complex mocks because the code fails to adhere to the dependency inversion principle. There is a massive engineering gap between code that is functionally complete, meaning it just runs in code that is verifiably robust. Without automated tests that actually validate the logic beyond the happy path, you are building a house of cards that will collapse during the first major framework upgrade or requirement change. Even if you manage to write the tests, do you actually know why the code was written that way in the first place? Let's discuss the loss of intent. In traditional software engineering, the why is just as critical as the how. We call this original intent. When a human developer synthesizes code, they balance requirements, security, and future-proofing. With AI-assisted development, we often bypass this synthesis entirely. The AI provides a complex regex, or a sophisticated recursive function that works. The developer accepts it with a click, and 3 months later, no one understands the underlying logic. This is the death of documentation. We aren't just losing comments, we are losing the mental model of the system itself. Software becomes a black box even to its creators. This leads to a state of legacy fear, where engineers are terrified to modify code because they don't grasp the AI's original reasoning. This structural rot eventually spills over into the actual runtime environment, creating immediate operational hazards in your production stack. The fourth mechanism of decay is dependency hell 2.0. AI models have a fixed training data cutoff. If you are building a system in 2026 using an LLM trained in late 2024, the AI will confidently suggest libraries and APIs that are now deprecated or, worse, contain critical security vulnerabilities. In a large enterprise, this introduces massive supply chain risk. The AI might recommend an old version of a JDBC library with a known bypass vulnerability or suggest using an AWS SDK method that was replaced for performance reasons. If your team is blindly pasting AI-generated package imports without verifying them against your organization's security governance, you are effectively opening a backdoor. We see this often in legacy modernization projects where AI hallucinates compatibility layers that don't exist in stable releases. Beyond security, there is a hidden cost in how these vibe-checked snippets actually perform under heavy production load. Vibe coding focuses on the vibe of the output clean indentation and readable variable names. However, readability does not equal performance. A common pitfall is the n+1 query problem, or O, n squared, complexity hidden within a sleek-looking loop. The AI might generate a beautiful Python list comprehension that looks elegant but performs a deep copy of a large dataset on every single iteration. Or it might suggest a recursive function for a problem that requires dynamic programming, leading to a Stack Overflow in production that never appeared during local testing with small datasets. As strategic consultants, we look for scalability bottlenecks. In an era where cloud costs are tied directly to compute cycles, these micro-inefficiencies generated across thousands of AI-assisted functions translate into millions of dollars in wasted operational expenditure. But why don't our senior developers catch these obvious flaws during the review process? The answer is psychological. The final mechanism of decay is review fatigue, when a developer can prompt 500 lines of code in seconds, but a human reviewer requires 30 minutes to truly audit it. A systemic bottleneck forms. To maintain velocity, teams start rubber stamping approving pull requests simply because the code looks professional and the AI-generated tests pass. This bypasses the most critical quality gate in the SDLC. Reviewers stop looking for subtle logic flaws and start looking for mere typos. This creates a dangerous false sense of security. In high-stakes enterprise environments, this erosion of the human-in-the-loop principle is the ultimate risk. By the time the decay becomes visible, the technical debt has reached a tipping point where a full rewrite is the only option. Now that we have diagnosed how AI breaks our systems, we must define the new rules for engineering, sustainable engineering principles. In the era of 2026, the traditional notion of prompting is being replaced by specification-first AI coding. The fundamental failure of vibe coding lies in the ambiguity of natural language. To build enterprise-grade systems, we must transition to intent-driven design where the human engineer defines what through formal specifications before the AI attempts the how. This involves using structured formats like YAML or specialized DSLs to define interface contracts, data schemas, and state transitions. By establishing these guardrails, we treat the AI not as a creative writer, but as a deterministic compiler of intent. This approach aligns with ISO/ISC 25010 standards by ensuring that functional suitability is baked into the initial requirements rather than being an afterthought. When the specification is rigorous, the AI's output becomes predictable and verifiable, reducing the entropy that usually leads to architectural decay. But how does this shift actually change the day-to-day workflow of a senior developer? The role of the engineer is undergoing a radical transformation into human-in-the-loop 2.0. We are moving away from being syntax writers who spend 80% of their time debugging semicolons and type mismatches to becoming system verifiers and architects of logic. In this new model, professional engineer focuses on cross-component consistency and non-functional requirements such as scalability and security. The AI handles the boilerplate and implementation details, while the human performs high-level validation against the business domain. This is not merely checking the code, it is a deep verification process that ensures the generated logic doesn't violate systemic invariance. We must utilize AI-driven observability tools to visualize how new code interacts with existing microservices. If the engineer loses sight of the big picture by trusting the vibe of a single snippet, the entire enterprise architecture risks fragmentation. But wait, if we are focusing on the big picture, how do we ensure the AI has enough context to actually be helpful? To maintain long-term system health, we need a technical stack that supports modular context management. Relying on a single, massive prompt is a recipe for hallucinations and token waste. Instead, sustainable engineering uses tools like the Model Context Protocol (MCP) and RAG-based codebase indexing to provide the AI with just-in-time context. This allows the AI to understand the relationship between a specific API endpoint and the global authentication middleware without needing the entire repository in its active memory. By modularizing our prompts and treating context as a versioned asset, we create a reusable knowledge base that evolves with the software. This infrastructure ensures that as the project grows, the AI's assistance remains grounded in the actual state of the architecture rather than drifting into generic patterns. But even with perfect context, how do we guarantee that the code produced is actually correct and maintainable? The first principle of high-quality AI engineering is AI-native test-driven development. In a vibe coding environment, testing is often skipped because the code looks like it works. In a sustainable methodology, we force the AI to generate the test suite before it ever writes a single line of production code. By using the AI to draft comprehensive unit and integration tests on our formal specifications, we create an automated truth machine. The AI is then tasked with fulfilling those tests, effectively trapping it in a loop of self-correction until the requirements are met. This reverses the usual flow where developers try to fix AI-generated bugs. Instead, the AI fixes itself against a human-defined objective. This test-first-generation approach ensures that the resulting code is not only functional but inherently modular and testable. However, does this focus on testing slow us down compared to the rapid-fire speed of vibe coding? Let's look at the data. Vibe coding offers an illusion of productivity. In the first few weeks, velocity is sky-high as AI churns out features. However, as the system grows, the lack of underlying structure leads to an exponential increase in technical debt, eventually causing velocity collapse. In contrast, sustainable AI engineering requires a higher initial investment in specification and testing. But because the code health remains high, the team maintains a steady, linear growth rate that eventually overtakes the vibe coders. We call this the sustainable break-even point. In an enterprise setting, where software lives for 5 to 10 years, the vibe coding path is as a financial liability. By prioritizing AI-native refactoring where the AI is constantly prompted to simplify and clean its own previous outputs, we ensure that the system remains scalable. But what happens when the next developer arrives and needs to understand why these decisions were made? The final pillar of sustainability is automated traceability. One of the greatest risks of AI coding is the loss of the why. AI can generate the how instantly, but it often leaves no trail of architectural reasoning. Professional engineers must use AI to document its own decision-making process. This involves generating architecture decision record DRs and intent logs alongside the code. By prompting the AI to explain the trade-offs it made, for example, why it chose a specific catching strategy over another, we create a searchable knowledge base for future maintainers. This transforms the AI from a black box generator into a transparent collaborator. In 2026, a piece of code without an associated intent record is considered technical debt by default. Now that we have established these core principles of specification, quality, and traceability, we are ready to look at the concrete framework that puts it all together. Let's move to the next chapter to explore the 2026 Professional Engineers Framework. In the enterprise landscape of 2026, the transition from vibe coding to engineered AI development begins with step 1 and 2, rigid design specification and constraint mapping. Before a single prompt is sent to an LLM like GPT-5 or Claude 4, a professional engineer must define the structural boundaries. This involves creating a comprehensive architectural decision record ADDR and formalizing interfaces using OpenAPI 3.1 or protobuf schemas. You aren't just telling the AI what to build, you are defining the mathematical and logical constraints within which it must operate. We map out data residency requirements, latency budgets, and specific library versions, such as ensuring compatibility with Spring Boot 3.4 or Next 15 features. This design-first approach prevents the AI from hallucinating architectural patterns that don't fit your existing stack. By treating the AI as an executor of a precise plan rather than a creative partner, we eliminate the ambiguity that leads to technical debt. But how do we actually transform these rigid specifications into working code without losing the speed that AI promises? This brings us to the core of our iterative execution strategy, which we will examine next. Step 3 focuses on modular synthesis through iterative refinement. The fatal mistake in vibe coding is requesting a complete feature in one go, which results in a monolithic, unreviewable mess. In the 2026 professional framework, we break development into atomic units, typically functions or classes that do not exceed 100 lines of code. We use chain of thought prompting integrated with local LSP data to generate code in small, verifiable modules. Each module is treated as an independent unit of work that must satisfy a specific subset of the constraints defined in step 2. This allows for continuous micro-refactoring, where the AI proposes a small change, and the engineer validates it against the module's interface. By utilizing tools like LangGraph to orchestrate multi-step code generation, we ensure that the output is not just a guess, but a calculated synthesis of the design specs. This modularity is the only way to maintain a high maintainability index in an AI-dominated codebase. Yet, even perfectly modular code can contain hidden logical fallacies. Payoff, this is why our next steps involving automated and human validation are the most critical part of the entire framework. The final stages, step 4 and 5, involve automated validation and a mandatory human semantic audit. In 2026, we don't just run unit tests. We employ AI-native validation engines that perform formal verification and static analysis using updated tools like SonarCube AI and SNCC. These tools check for common AI smells such as redundant logic or insecure package versions. However, the automated layer is only the first shield. Step 5, the human semantic audit, is where the professional engineer earns their title. This is not a traditional code review. It is an investigation into the intent behind the code. The engineer must verify that the AI's implementation doesn't just pass the tests, but also adheres to the long-term architectural vision and business logic nuances that an LLM might miss. We look for shadow depth code that works now, but will break during the next scale-up or migration. This dual-layer validation ensures that the velocity of AI-assisted development does not compromise the integrity of the enterprise system. This concludes our 5-step model, but how do we decide when to apply such a rigorous process versus a quicker approach? TSER, the enterprise decision matrix, in the next section will provide the answer. To manage AI-assisted development effectively, enterprises must adopt a decision matrix that differentiates between vibe and engineered AI. Not every project requires the full 5-step framework. For internal low-risk tools, such as a one-off data migration script or a prototype dashboard, vibe coding characterized by high velocity, prompt TV generation is often acceptable and cost-effective. However, for core systems that handle financial transactions, user PIE, or critical business logic, we must mandate engineered AI development. This matrix evaluates two primary axes: business impact and system complexity. High impact, high complexity projects sit in the zero vibe zone where every line of code must be justified by a specification. This strategic categorization prevents the organization from over-engineering simple tasks while ensuring that the foundations of the enterprise remain unshakable. Using this matrix, team leads can allocate their most experienced human auditors to the zones where they are needed most. But what do we do with the systems already built during the vibe gold rush? Question: can we use AI to fix the very problems it helped create? The reality for many IT leaders in 2026 is a mountain of legacy vibe debt codebases generated in 2024 and 2025 without proper oversight. To address this, we use the AI refactoring stack. This involves deploying specialized LLM agents designed specifically for debt remediation. These agents analyze existing code against modern architectural standards and suggest refactoring patterns like the strangler fig for monolithic AI-generated functions. We aren't just cleaning up syntax, we are re-injecting structure into unstructured code. This process includes inferred specification, where the AI looks at the messy code and tries to document the original intent, which a human engineer then corrects and solidifies. This backward engineering is essential for regaining control over systems that have become black boxes. By systematically applying AI refactoring, we can transform a high-maintenance vibe mess into a sustainable, engineered asset. But tools alone won't solve the problem if the team's culture remains stuck in the vibe mindset. Teaser: how do you evaluate if your team is actually falling into these traps? Let's look at the leadership checklist. To conclude this chapter, we provide a checklist for engineering culture and tooling choice. As a team lead or architect, you must monitor specific signals that indicate a slide back into vibe coding. Are your developers spending more time prompting than reviewing? Is the review to merge time for AI-generated PRs suspiciously low, suggesting that no real audit is happening? In 2026, a healthy engineering culture is one where AI assistance ratio is balanced with review depth. We must select tools that provide transparency ID extensions that track where code came from and which parts were modified by humans. If your team cannot explain why a piece of AI-generated code works, you have already lost the battle. This checklist serves as a guardrail to ensure that while we embrace the speed of AI, we never surrender the rigor of professional engineering. In our final chapter, we will move beyond these frameworks to look at the future of quality itself. Bridge next, we explore beyond the vibe, the future of quality and how AI will redefine what we call perfect code. As we conclude this journey, we must internalize the 3 golden rules of the 2026 AI-assisted development framework. First, spec-first development is no longer optional. It is the constitutional foundation that prevents AI from hallucinating architectural inconsistencies. By defining interfaces and behaviors before a single line of logic is generated, we establish a verifiable contract that the LM must follow. Second, small module architecture limits the blast radius of AI-generated bugs, ensuring that components remain human-readable and easily replaceable without cascading failures. Third, a test-driven approach provides the automated safety net necessary to validate that vibe-based iterations do not break existing enterprise logic or violate IISC 25510 quality standards. In the age of large language models, these engineering rigors are the only thing standing between a scalable system and a legacy nightmare of unmaintainable code. We have moved from the era of manual syntax writing to the era of logic orchestration, which requires a level of precision that transcends simple prompts. But does this transition mean the human element is being marginalized in the modern development lifecycle? Question next, we will look at why the expertise of a professional engineer is becoming the most critical bottleneck and value driver in the AI era. The rise of vibe coding often leads to the misconception that deep technical expertise is losing its value. In reality, the opposite is true. As AI lowers the barrier to entry for generating syntax, the industry will see a surge in vibe-heavy, but architecturally fragile systems. This is precisely where the information management professional engineer's eye for system integrity becomes the ultimate differentiator. Your role is evolving from a builder of code to a high-level auditor and architect who ensures non-functional requirements like scalability, security, and maintainability are not sacrificed for speed. The ability to look at an AI-generated module and immediately identify hidden race conditions, API version mismatches, or security vulnerabilities is a skill that remains a human-led premium. In 2026, the true competitive advantage lies in verification over creation. We are entering an era where being able to define what is correct is far more valuable than knowing how to write it. By mastering the frameworks we discussed today, you transition from being a prompt user to a strategic guardian of enterprise architecture. Payoff: the era of vibe coding is just the beginning. The real mastery begins when you turn that vibe into a verifiable, engineered reality that stands the test of time.